Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So, imagine you have this heavily engineered, multi-$1,000 gearbox, right? You've calculated all the macro geometry, the bending moments are perfect.
Oh yeah, the finite element analysis looks absolutely pristine on the screen.
Exactly. But then, the very first time you fire it up under full load in the field, the primary drive shaft just violently shears in half, and you're left wondering, well, why?
Right, and the answer is usually some microscopic sharp corner that everyone just sort of ignored.
Yeah, and that's our mission for this deep dive today. We are pulling from some pretty heavy structural analysis texts, specifically looking at the brutal physics behind notches, miscellaneous design elements, and fatigue failures. We're basically dragging torsional shear out into the light.
Which is so necessary. I mean, we spend so much time obsessing over bending stresses, but twisting forces interacting with tiny geometric features like keyways and splines, those are the silent killers. They're what's actually shredding gearboxes out there.
Right, because bending is visual, you can physically see a beam deflect, but torsion...
Torsion is invisible. It's this internal twisting mechanism that acts, well, it acts a lot like water under immense pressure. It just aggressively hunts for the path of least resistance.
Oh, wow.
Yeah, it exploits every single microscopic flaw, surface scratch, or sharp corner in a piece of steel. And the texts we're looking at make it very clear that the math of these twisting forces is just completely unforgiving.
So if you're listening to this and you want to understand why a shaft that looked theoretically perfect on paper suddenly rips itself apart, you can't just look at the macro scale. You really have to zoom way, way in to the microscopic battlegrounds, right? Like key ends and fillets.
Absolutely. You have to get down to the micro level.
So let's start at the most basic geometric disruption you can introduce to a perfectly smooth shaft, the key seat. Before we even get to the catastrophic failure part, we have to look at how simply carving a trench into the steel amplifies that torsional stress.
Right, because you're literally removing material from the most stressed part of the shaft.
Exactly. And manufacturers typically use two main types of keyway ends. You have the sled-runner, which is exactly what it sounds like. The machining curve glides up gently at the end, kind of like the tip of a winter sled.
Yeah. Very smooth transition.
But then you have the end-milled key seat, which is just a sudden, aggressive, semicircular bowl cut vertically right into the material.
And the way torsional stress flows around that end-milled semicircular bowl is just purely chaotic.
How so? Like, what does the math actually look like there?
Well, okay, so in a perfectly smooth, straight section of a U.S. standard key seat, the stress map is, relatively predictable. The maximum shear stresses operate neatly in the longitudinal and perpendicular direction.
Okay, that makes sense.
Right. And the maximum normal stresses, those are the forces trying to pull the metal apart or crush it together. They share the exact same magnitude as that shear. But they act at these perfectly predictable 45-degree angles to the shear plane.
But I'm guessing the moment that torsional force hits that semicircular bowl of an end-milled cut, that whole predictable map just gets thrown out the window.
Oh, completely. It gets obliterated. The maximum normal stress suddenly becomes tangential, and it locates itself exactly 50 degrees from the axial direction.
Wait, 50 degrees, not 45.
Exactly 50 degrees. And the maximum shear stress shifts to sit at a 45-degree angle to that normal stress, operating at exactly half its value.
Man, it's exactly like a high-pressure river channel. If you have a deep, straight trench, the water flows fast, but it's uniform, right?
Yeah, nice and laminar.
But if you suddenly terminate that trench in a rounded bowl, the water doesn't just stop or flow smoothly around the rim. It crashes violently. It creates these turbulent, chaotic eddies that pool up massive amounts of kinetic energy at very specific points.
That's a great way to put it. The geometric discontinuity acts as a literal dam. The stress flow lines, which normally want to travel parallel to the outer fibers of the shaft, they are forced to bunch up incredibly tightly just to get around that sudden bowl.
And in our shaft, that energy basically pools at that highly localized 50-degree mark. Boy, let me push back on this a bit.
Sure.
If these stresses pool up so chaotically at these awkward angles, like, creating this massive weak point and huge localized stress multiplier, why do we even use end-milled semicircular key seats? Like, why not just let the geometry flow naturally with the sled-runner?
Well, because the sled-runner geometry allows those stress flow lines to spread out over a longer, gentler curve, which dramatically reduces the stress concentration.
Right, so it's clearly better mathematically, so why don't we always use it?
Well, it comes down to the eternal compromise between theoretical physics and brutal factory floor economics.
Of course. Money.
Always. Dropping an end mill straight down into a piece of shafting is incredibly fast. It requires one simple tool path, it's cheap, and it's endlessly repeatable for mass production.
Whereas cutting a perfect sweeping sled runner requires a whole different milling setup, right?
Exactly. Different cutter, different setup, way more machining time. So we're basically stuck with the end mill geometry for economic reasons.
So we are intentionally introducing a massive flaw into the system just to save a few cents on manufacturing.
That's the reality of it, yeah. And because we do that, mapping these precise angles mathematically, like knowing exactly where that 50-degree tangential stress is going to hit, is the absolute only way to predict where the fracture will eventually begin.
Wow. Okay, so a theoretical key seat sitting empty on a textbook page is one thing. But to understand real gearbox destruction, we really have to look at what happens when you actually transmit torque through a key.
Right, because an empty slot doesn't do any work. The moment you hammer a physical steel key into that slot and mate it to a hub, you alter the entire mathematical boundary condition.
Because the load doesn't simply enter the key uniformly, does it?
Not at all. It enters heavily at one end and exits at the other. That creates a severely non-uniform distribution of force across the entire length of the metal.
And the structural analysis texts highlight something really fascinating here about how we even know this. They didn't just run computer simulations back in the day. They used the electroplating method.
Oh, yeah. This is brilliant engineering history right here.
Right. They actually took a steel shaft, carved a key seat with a key length of 2.5 times the diameter of the shaft, and then coated the entire assembly in a microscopic layer of copper.
Yeah. And when they applied immense torsion to it, the underlying steel strained and the copper plating actually yielded.
Which is insane to think about. It physically changed appearance in real time. It basically acted like a visual heat map of the invisible stress concentrations.
It's such a clever test because it physically proves that simply inserting the key fundamentally changes the theoretical math and the fillet stress concentration factors.
Yeah. So the math for an empty keyway is just totally invalidated once the key is in.
Exactly. And the most critical variable that dictates how those stress lines map out isn't necessarily the sheer strength of the square key itself.
Wait, really? Then what is it?
It's the degree of press-fit pressure between the shaft and the hub.
Okay, let me ask a clarifying question here, just to push back on that a bit. If the press fit is doing so much work, does the physical steel key itself actually bear the load, or is the friction from the tight press fit doing the heavy lifting?
It's all about friction. Friction is paramount here. I mean, and think about it when you apply a heavy press fit. The intense static friction between the outer diameter of the shaft and the inner diameter of the hub basically locks them together.
So they effectively act as one continuous solid piece of metal.
Exactly. The torsional force traveling down the shaft doesn't even see the microscopic gap of the keyway. The force just passes straight through that friction boundary.
Oh, wow. So the theoretical stress curves from the textbook shift dramatically the moment that physical contact pressure is introduced.
Completely. The friction changes the entire game.
So the key is basically just a mechanical backup parachute. Like, as long as the static friction holds, the stress bypasses the sharp corners of the keyway entirely.
Yep. But the second that torque spikes above the frictional holding force, say you have an emergency stop or a jammed gear, the hub slips.
And then what happens?
That massive rotational shock load suddenly crashes directly into the side of the keyway, and all those chaotic stress pools we mapped out earlier, they get supercharged in a fraction of a second.
Man. And knowing where that stress pools naturally leads to the ultimate consequence, which is how these forces literally tear the metal apart over millions of cycles through fatigue.
Yeah, fatigue is brutal. And the research indicates that torsional fatigue in these microscopic features is a distinct two-step process.
Right. So the failure is initiated by sheer stress, but the eventual crack, like physical separation of the steel lattice, is driven entirely by normal stress.
Exactly. And there are two primary battlegrounds where this 1-2 punch plays out.
Okay, break those down first.
First, you have the key seat fillet, which is that incredibly tiny radius at the very bottom corner of the trench. And second, you have the surface of the semicircular keyway end, which, relatively speaking, has a much larger radius compared to that tiny bottom fillet.
So in pure torsion, the sheer stress damage, the initiation phase that typically starts deep down in the fillet, right?
Usually, yes. Because the radius is so small, it creates a massive localized stress spike. However, the stress gradient down in that fillet is incredibly steep.
And by steep stress gradient, you mean that the energy is insanely high right at the microscopic surface of the curve, but if you move just like 1 millimeter deep into the steel, the stress just drops off a cliff.
Exactly the case. The energy is incredibly violent, but highly localized. Now, compare that to the surface of the semicircular end.
The larger radius.
Right. The radius there is larger, so the peak stress doesn't spike quite as high, but the gradient is shallower, so the stress penetrates and affects a much larger volume of the surrounding material.
Oh, interesting. So depending on the exact load profile, the surface could actually initiate the failure before the fillet even does.
Exactly. It's a race to see which stress profile gives way first. But regardless of whether the crack starts deep in the bottom corner or up on the surface, once that initial microscopic fracture forms, the final direction the crack travels is dictated entirely by the high normal stresses.
Because they're the forces actively pulling the material apart.
Yeah.
It's exactly like splitting a massive cord of wood. You know, the shear stress is your wedge. It's that sharp, highly concentrated force that you drive in just to make the initial microscopic dent in the grain.
That's a really good analogy.
Yeah, and then the normal stress is the sledgehammer. It doesn't make the dent, but it transfers massive energy into that existing vulnerability, catching the edges of the wedge and violently splitting the log wide open.
Yep, the wedge starts it, and the sledgehammer finishes it. And when these forces interact poorly due to a design flaw, you see a very specific catastrophic failure mode.
The peeling failure.
Oh yeah. The texts note that torsional fatigue starting down at the fillet frequently develops into this severe peeling type of failure.
It's wild to visualize. Like when you pull a disassembled shaft out of a broken gearbox, it literally looks like a thick strip of the solid steel has been peeled back along the length of the shaft, almost like a banana.
It really does. And observing that peeling failure is like walking into a forensic crime scene.
How so? What does it tell you?
It tells the reliability engineer exactly where the initial design failed to account for that steep stress gradient. I mean, if the metal peeled, the shear stress at the fillet acted as the wedge. But the normal stress caught the microscopic lip of that crack and ripped it longitudinally down the shaft.
And this usually happens because, the key was transferring the torsional load unevenly? Or maybe a machinist used a cutter with a smaller than standard fillet radius?
Usually the latter, yeah.
Ah.
Creating a corner that is just way too sharp for the stress to flow around.
So, if a single keyway creates a microscopic battleground volatile enough to peel solid steel, the logical next step is exploring splines.
Oh boy. Splines. The multi-tooth torsion nightmare.
Seriously. You are basically taking a single geometric stress razor and multiplying it symmetrically around the entire circumference. It fundamentally alters how the entire cross-section of the shaft handles twisting forces.
It does. And to quantify just how volatile a spline is, the sources highlight this really brilliant three-dimensional photoelastic study by Yoshitake on an 8-tooth spline.
Photoelasticity is so cool, they basically took a plastic model of the spline and passed polarized light through it while applying torque, right?
Right, because the polarized light actually bends as the plastic strains. So it allows engineers to visually see and measure the otherwise invisible stress concentration lines.
And what Yoshitake found was just staggering.
It was. For an open involute spline, and by open I mean they were testing just the shaft itself, with no mating hub attached using a full, mathematically ideal fillet radius, the torsional stress concentration factor reached 2.8.
That's referred to as KTS, right? 2.8. Just by cutting those 8 teeth into the shaft, even with perfectly rounded, smooth fillets, you are nearly tripling the shear stress at the root of every single tooth compared to a smooth shaft of the same diameter.
Nearly tripling it. And remember, that 2.8 multiplier is just a theoretical baseline under perfect laboratory conditions. Real-world application changes the physics entirely.
Because it's never an open spline in the real world. It's always mated to something.
Exactly. When Yoshitake tested this spline with a mated pair, where the fitted length of the hub was slightly greater than the outside diameter of the spline itself, the load dynamics shifted completely.
In what way?
Well, the maximum longitudinal bending stress located at the end of the individual tooth became numerically about the same as the maximum shear stress.
Wait. We're talking about purely twisting the main shaft here. Where's the bending coming from?
It happens because the mating hub and the shaft have different stiffnesses, so they twist at slightly different rates. The load doesn't distribute perfectly evenly across the tooth surface.
Oh, so the hub actually grabs the far ends of the spline teeth and pries them sideways.
Exactly. It treats a feature designed purely for torsion as a miniature diving board. So you have maximum shear from the torque and massive bending forces from the mating interference attacking the exact same microscopic boundary layer at the root of the tooth.
That is horrifying. And the mathematics governing that root fillet are terrifying too. The sources detail a mathematical analysis of a theoretical shaft featuring a number of longitudinal semicircular grooves.
Yeah, the math doesn't pull any punches here.
Right, the equations prove that as the ratio of the fillet radius to the shaft diameter approaches zero, meaning as that root fillet gets sharper and sharper, the stress concentration factor intrinsically approaches too.
Which is a huge problem on the manufacturing floor.
I mean, it's essentially like perforating a piece of paper, right? Or creating the sharp folds on a piece of corrugated cardboard.
Let me push back on this. If the stress multiplier shoots toward 2 as the radius shrinks, is cutting a spline essentially just designing the shaft to shear itself along a dotted line if the machining isn't perfectly rounded?
That is a completely valid concern, and basically, yes. Proper, generously machined fillet radii are the absolute only things preventing splines from acting like perfectly engineered self-destruct mechanisms under heavy torque.
Wow.
Yeah, the mathematical floor dictates that a sharp internal corner under torsion will always at least double your stress. So if a machinist uses a worn tool insert, or even worse, if a drafter fails to specify a large enough radius on the manufacturing print, that dotted line effect takes over.
And the stress concentrates so heavily at those microscopic sharp corners that the shaft will simply unzip itself the first time a shock load hits the drivetrain.
Unzipping a shaft is a horrifying visual. It is for anyone who maintains heavy machinery. But it really drives home exactly why understanding the behavior of these tiny fillets, these 50-degree keyway angles and spline stress multipliers, is so critical.
It really is the absolute difference between a gearbox that runs for 20 years and one that spectacularly detonates on day one.
Because you can get the macro calculations perfect, and you can over-engineer the overall shaft diameter all you want, but if you ignore the localized microscopic stress pools, the design is just going to fail.
Period. The physics of torsion do not care about the macro scale. They exploit the micro scale.
So to wrap this deep dive up, I want to leave you, the listener, with a final provocative thought about the reality of combined loading. We've spent this entire time mapping out pure torsion.
Which is rare in isolation.
Right. In the real world, shafts bend while they twist. The sources provide a nominal stress equation for combined bending and torsion, and without reciting a wall of raw math, the formula conceptually squares the ratio of torque to bending moment. It basically reads as 16m divided by pi times d cubed multiplied by the quantity 1 plus the square root of the quantity 1 plus the square of the ratio t over m.
And the physical reality of that equation means that bending and torque don't just add together linearly.
Yeah.
They compound each other exponentially inside the steel lattice.
Exactly. We just mapped out exactly how a purely torsional fatigue crack initiates with a shear wedge in the fillet and propagates longitudinally when the normal stress sledgehammer catches it.
Yep.
But ponder this. How does adding a sudden, unexpected bending moment from a badly misaligned gear totally rewrite the path of that torsional fatigue crack we just mapped out? When a massive bending spike compounds that squared ratio in the formula, how violently do the wedge and the sledgehammer change directions inside the metal?
It's definitely something to visualize the next time you hear a heavily loaded gearbox whining on a factory floor.
Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. It takes you a few seconds, but it tells me this workbench is worth keeping open.